And then the last presentation will be about the case in Maceió. You're going to present that. Very nice. What's your name?
Magdalena.
Ah, yeah, Magdalena. Okay. Would you like to use the microphone or?
I would try, yes.
This
One,
yeah,
okay. And this?
That is forward.
Oh, no?
No, this is, well, maybe
Sorry.
here.
Okay.
That is
the pointer. Oh, it's very
one
difficult.
forward.
Yes.
Does it work?
This is not, no, this is...
No, the big one is forward.
Ah,
the
okay.
white one.
Yes.
Yeah. Good.
Okay. So, good afternoon, everyone. My name is Magdalena Vassileva, and I'm a PhD student from the University of Hanover, but based in the Geoscience Research Institute in Potsdam, Germany. And today I'm going to bring you to Maceió, Brazil, which is this region here. Is the capital city of Alagoas State, which is located in the northeast region of Brazil. Has beautiful beaches, so I really recommend to go there and check it. But it's located on the Sergipe-Alagoas salt basin. So in 76, they found that there's a salt laying down, down the city, and they start to extract it. So in this, since 76, 35 wells, salt wells have been built. And in 2018, 7 of these wells were still active. And what happened? Okay, so this is how salt wells looks like. And you can see that here are all houses where people live, and therefore the salt extraction happens exactly inside the urban area. And in February 2018, there were very heavy precipitations, and there was also registered a seismic shallow shock, seismic shock. And after these two events, actually many cracks and sinkholes appeared inside this neighborhood of Pinheiro. And you can see some images from 2018. And so what happened that after that, between June and April 2018-2019, the Brazilian Geological Survey was called to make an investigation about the causes. And after 1 year of survey, they used different in situ techniques like geological survey, geophysical and geotechnical investigations. They also produced, or someone produced produced some INSAR analysis, but just 1 year of data set, and they conclude that actually the subsidence was a result of destabilization of the salt cavities. So in March 2019, the municipality of Maceió declared a state of calamity, and the second half of 2019, all salt extraction have been stopped. In January 2020, there was an agreement reached between the mining company and the authorities for a financial compensation and a relocation program for the victims. And in 2020, there started some processing to fill the cavities with sand. And in all this, it was kind of a huge topic in all journals, because of course the salt mining company, they refused to acknowledge responsibility, and until now they are still kind of trying to demonstrate that the salt cavities are not the main causes of this subsidence. And this is where we come from. So we actually were involved in this study in a very indirect way. Someone called in GFZ in our institute, and we are, as a research team dealing with INSAR, were involved asked to analyze the available SAR data and check what's going on and what happened in the past years. So we took all the data set we found, and we tried to analyze the displacement and derive the dynamics of this process in the last period. And we also integrated with some numerical modeling to understand what was causing these deformations really. So I will start with some SAR data, so INSAR analysis. So this was my SAR data set I used. There's a huge gap between 2011 and 2015, but actually wasn't a big deal because I just interpolate them, and it was pretty good result. And you can see the difference between the first data set with very low density, temporal low density images, and after that Sentinel-1 providing very high density data set. These are the first results. So to combine the different platforms and datasets, I just projected all the displacement into vertical displacement. And here is a cumulative map of three different periods. You can see how the main subsiding area is increasing in intensity and magnitude. Here are two profiles. I hope it's much visible because I can't see it very well from there. But so you can see that actually the displacement in the second part of our dataset was increasing, accelerating much more than in the first period of time. And we also find, no, sorry, I make a mistake. Sorry. Yes, I go back. So we also find this second subsiding small region, but actually this region is showing a different type of subsiding. It's more like block caving subsidence. And it was also interesting to highlight this other subsiding region. And if we look at the time series, so I took two main points, 1 point in the main subsiding region, 1 point in this second subsiding region. And we can see that what I was explaining before, at the first stage, this region was already subsiding in 2004 with very little rate, like 3 centimeters at the beginning, then 5, that was slowly increasing. In 2011 was reaching around 13 centimeters per year. And until 2016, there was another acceleration to 20 centimeters per year. And there was a huge acceleration after this precipitation period sorry. No, I lost again. I'm sorry. Yeah. Okay, I just go. Yes, so you can see that there was a huge acceleration in displacement rate. Means that actually the precipitation, they were somehow influencing the subsidence process that was happening. And since 2020, we can see instead some kind of deceleration trend. And this is also maybe contributed to these new activities of filling the cavities with sand, maybe. But we need a longer time series to be sure about that. And we also had for certain periods of time ascending and descending data set. So we combine them together to derive vertical and horizontal components. So you can see these are kind of average values for several years. And you can notice that the areas with main horizontal displacement are kind of shifted compared to where the main vertical displacement is happening. And this also coincides with the areas where most damages were found and more cracks. So we use these datasets from ascending and descending orbit geometry to derive some geophysical modelings. We use point source and rectangular crack models. I hope you are kind of familiar with those models. They're mainly used for volcanotectonic studies. And we apply them here to try to derive what kind of source was provoking the subsidence that we were observing on the ground. And this is the result. From the middle figure, you can notice that kind of the location. So we actually derived the source locations for year-based dataset. So this is kind of the evolution of the source, starting from 2015, 16, 17, 18, 19. And you can see that from the horizontal point of view, the source is quite stable. So the source is not moving horizontally. But if we look at the vertical, so at the depth of the source, we can see some kind of upward movement, upward trend of the source during these years. And this can be explained, or we explain it, because of the geological survey. They produced some technical reports that were publicly available, and we find that actually it was detected that some of the cavities, they moved upward during the years, but unfortunately there are not so many measurements available and not for all cavities. Going to the next modeling, numerical modeling we applied is a distinct element model. And in this case, we wanted to simulate the behavior, the geotechnical behavior of the cavities, of possible cavities, considering this layer, stratigraphic layer geology. And we took two real size cavities. Specifically, they are indicated in this map. So these two cavities. So we simulated how these two cavities behave in time, considering the real geological stratigraphy of the region. And if we go to the results, we used two pressurized conditions, one pressurized condition or working condition and one depressurized conditions. Means that at the beginning we injected this pressure, like hypothetical pressure, to the cavities, and we simulated their behavior. And we saw that actually the behavior is very similar with just few differences, mainly in timing. So the stages in case of the depressurized scenario, so lower pressure inside the cavities, are reached much faster compared to pressurized scenario. And also in the case of depressurized scenario, both cavities are collapsing, and in pressurized scenario, only one cavity, the shallower cavity, collapsed, and the other is only destabilized. And this is what happened on the surface. So again, in the first case, in pressurized scenario, we have kind of lower rate subsidence compared to the second case, but still is of 1.5 meters. And you can see the plotted INSAR measurements on this on a 1D profile. And in the case of depressurized scenario, we can see that the displacement on the surface is much larger, and there's also some kind of discontinuities which we associated to sinkholes formation. And our work was published in 2021. And I want to also tell you some stories about what happened next. So it get kind of interest from the German side. So we also have interviews from a German, very important German newspaper, Süddeutsche. And so it got a lot of interest in the German side, but also from the Brazilian side. So we were contacted from the civil defense, and they were very interested in our work. So we were invited there to see and visit the affected areas, and to see also the activities they were going. And one of them was this monitoring system, 24 hours per every day, so constant monitoring system, which were checking different parameters around the area. And we also visit these cavities and filling spots, and which is a very time-consuming procedure, because to fill one cavity is more or less 100,000 cubic meters, and it took like 9 to 10 months to just fill one cavity, and we're talking about 35 cavities. So it's going to be, and they're doing it one cavity per time, so it's going to be a very slow process. Which is important to monitor using INSAR and other instruments to see if really something is happening, or how the terrain is reacting, how the subsidence is being stopped using this procedure. And and we witnessed actually this ghost town, because now As you can see, all this red region was a region that have been evacuated, means that all people, almost 16,000 inhabitants have been displaced at this region. And now is just walking in empty streets and empty buildings. And there's a lot of destruction, which is not due to the subsidence, but because people, when they left, they took all the material they could utilize again or recycle again. And also, of course, there are some criminalities that they were going and looting the spots. And it was very unrealistic scenario. And this is another image from above, from a drone. And it's very impressive, the social impact that this event had in Maceió. And what happened is that each resident was recompensated because each house received kind of the same amount of money, and they were kind of displaced to a temporary place first, and then they were left to decide where to go and to find their way and to find their new house. So if they want to buy a new house in another part of the city, or they just want to leave the city, or they were free to decide. So there was not a regularity in this. And of course, what happened is that 60,000 people in a city of 1 million of people created like a boom of the price of housing. And therefore this created another problem for all the city. And it's a touristic city, so therefore the speculation is a lot. And now the worry is what is going to happen with all this area. And the interesting fact is, or the bad or sad fact is that all the houses now, they are property of the mining company. So kind of will decide, maybe together with the authorities probably, what is going to be the future, but probably a lot of speculation will happen in the future. And I just discovered that in 2021, actually, some residents from Maceió, they came to Netherlands and they sued a company here. And now there's a case going on in Netherlands and asking for justice. And I just want to leave you with these photos from my colleagues, our colleagues from the civil defense, of some messages that the residents of the area left behind. And I'm open to your questions. Thank you.
Very impressive, Magdalena. Any responses, questions? Yeah.
Yeah, thank you very much for this very nice case study. It reminded me what happened in Lorraine area also, with this relation about social economic interaction with subsidence, very important things with money. About the vocabulary, you use sinkhole for describing subsidence. So I'm wondering, it's really sinkhole or look like more subsidence when I look for the curves. So can you highlight this one?
Yes, here. So yeah, one thing is the subsidence, which is this more big trend. So this is the subsidence, but then there's also local spots which are also have been detected or witnessed. So for instance, this here, this is a sinkhole for us, in our case, in our understanding. So it's kind of a local spot that creates a cavity due to some more local geology. And
we define that as crevasse.
Crevasse, okay.
And not sinkhole, because the description of sinkhole is more or less different. And in subsidence like that, we have this phenomenon crevasse upgrades, and we define this one as hazard.
Okay.
My second question related to the treatment. You if I understand well, they will fill the cavity at 1,000 meter
Yeah.
depth.
Yes.
It's economically, there are some studies to see if it's a benefit or not, because we never, in my opinion, feel cavity at this depth in mining there.
Okay, probably they have been studied options, but this is all in hand of the mining company. So they're doing everything by their own. They're just giving reports back to the authorities, which are not public, of course. So it's very difficult to get to those data. But this was their proposal, plan proposal. And of course, authority, they accepted it. So I don't have details on it. And yeah, they're not publicly available. No,
Okay.
thank you for the questions.
Any further questions? Kai?
Yeah, very impressive work. I was wondering when it goes to court and you really need very concrete evidence. Is it also deciding to do this to actually see if there was a collapse or something like that? It might be reversed, right? If a big structural building like yours is a limestone roof, for instance, then you should see it.
Geophysical, you mean? I mean, they use geophysical analysis, geophysical sensing in this year, only between 2018. They made some campaigns, but up to now, they're not using it anymore. They just installed some GPS stations, GNSS stations, and some seismic stations, which are constantly monitored. And yeah, they received INSAR analysis because it's kind of very complicated because the civil defense, they receive all the data from outside, so they don't have capacities inside or skills inside. So they received reports and yeah, information from outside, so they don't process the data themselves, and therefore it's kind of yeah, you don't have freedom also in this deciding, and we can't just go there and do it.
Okay. Any final question? No, then I think it's time for our coffee break. Thank you very much again.
Thank
for your
you.
presentation.